In this section, we'll learn about recursion. We'll see how to write recursive definition for a given problem and how to trace recursive algorithms. Recursion is a process in which a problem is solved by repeatedly breaking it into similar but smaller problems. The smaller problems can be easily solved and the solutions are used to find the solution of the original problem. In programming languages, recursion is implemented through recursive methods. A recursive method is a method that calls itself inside its own definition. For example, this G is a recursive method because there is a call to G inside its own definition. Now when this G is called in another method F, its code will be executed. And in the code of this method, there is a call to G. So again G will be executed. So this F calls G, again G is called, again G is called, and it seems that this process will continue forever. But in practice, recursive methods are written in such a way that at some point recursion terminates and method calls start returning. The case in which this method will not be calling itself is the base case. Now we'll see how to write recursive methods. We've seen that recursion is a process in which a problem is solved by breaking into smaller versions till we get the smallest version which can be easily solved. The smallest version is the base case. Now to write a recursive method, we need to do these two things. Identify the recursive case and identify the base case and its solution. Now to identify this recursive case, we need to think how we can break our problem into similar type of a smaller problem. And this base case is the case in which the problem can be easily solved. So we have to identify the base case and find solution of the problem in this case. If we don't define a base case, then we'll have infinite recursion because the recursive method will keep on calling itself. We can have more than one base case in a problem. We should write a recursive method in such a way that with each recursive call, we come closer to the base case and we finally reach the base case. A solution of the base case is known to us. So we'll apply the solution of base case to find solution of our original problem. In this video, we'll see how control is transferred in recursive method calls. But before that, we'll see transfer of control in normal non-recursive calls. This method F is called inside this method. Now inside F, this method G is called. Inside G, this method H is called. Now when this method H finishes executing, the control is transferred here to this statement following this method call. When this method G finishes executing, control is transferred here because the return value of G has to be assigned to X. Now when this method F finishes executing, then the control is transferred to this statement following this call. So we can see that when a method finishes executing, the control is transferred to the caller method at the place where we had left it. In recursive methods also, the control is transferred in the same way, but there the method being called each time is the same. Suppose this method F is a recursive method. We'll call the different calls of this method as different invocations of F. Now first time when this method is called, the value of n is 3. Now here F is called with argument n minus 1. N is 3. So next time this F is called with argument 2. Now in this invocation, value of n is 2. Similarly, in the next invocation, value of n is 1. Now this condition is true. We have reached the base case. So we'll return here. Now when this invocation finishes executing, we'll return here to this statement following this call. Similarly, when this invocation finishes executing, we'll return here. So we can see that as in non-recursive methods, here also, when execution of an instance of a method finishes, we return to the previous instance where we had left it. All the instances of a recursive method are different. And for each instance, a new set of parameters and local variables is created. Recursive methods work in two phases, binding phase and unbinding phase. Winding phase starts when the recursive method is called for the first time, and it continues with each recursive call. It stops when the base case is reached. And when this winding phase stops, this unwinding phase starts. So unwinding phase starts when the base case is reached. And in unwinding phase, all instances of the recursive method return in reverse order. And this phase stops when first instance of recursive method returns. Now in this example that we have seen earlier, the winding phase starts here when the method f is called for the first time, and it stops here when the base case is reached. From here, the unwinding phase starts. So this piece of code that is before the recursive call is executed in the winding phase, and this piece of code that is after the recursive call is executed in the unwinding phase. So in a recursive algorithm, if we need to execute some code while returning from method calls, we can place that code after the recursive call so that it is executed in the unwinding phase. In this video, we'll see how to find out the factorial of a number recursively. Factorial of a number n is defined as the product of numbers from 1 to n, and it is denoted by this exclamation mark. Now factorial of 5 is product of numbers from 1 to 5. We can write factorial of 5 as 5 into factorial 4 because factorial 4 is the product of numbers from 1 to 4. Similarly, we can write factorial 4 as 4 into factorial 3. This factorial 3 can be written as 3 into factorial 2. This factorial 2 can be written as 2 into factorial 1. And this factorial 1 can be written as 1 into factorial 0. Now this factorial 0 is 1. So this acts as a base case and this is the recursive case. We know the solution of the problem in this case. So we can apply this solution to find the solution of our original problem. We'll place the value of factorial 0 here. We'll get the value of factorial 1. We'll place the factorial 1 value here and we'll get the value of factorial 2. And finally, we'll get the value of factorial 5. Now this is the recursive definition of factorial. We have defined the solution of the problem in terms of the problem itself. The problem of finding this factorial n minus 1 is similar to that of finding factorial n but smaller in size. This is the recursive method for finding factorial of a number. If n is 0, 1 is returned. Otherwise, n into factorial n minus 1 is returned. Now let's trace this method. First, we have called this method with argument 3. So in the first call, value of n is 3. Now this method is called with argument n minus 1. n is 3. So this is called with argument 2. So in the next call, value of n is 2. Similarly, in the next call, value of n is 1. And in the next call, value of n is 0. Now this condition becomes true. We have reached the base case. So this winding phase will stop and unwinding phase will start. So this 1 is returned from here. Value of this call is 1. N is 1. So 1 into 1 is returned from here. Value of this call is 1. N is 2. So 2 into 1 is returned from here. Value of this call is 2. N is 3. So 3 into 2 is returned from here. So this is how we find out the factorial of a number recursively. Now let's see this method in a program. This is the method for finding factorial of a number recursively. In main, we have called this method here. Now let's run this program. In this video, we'll see how to print numbers from 1 to n recursively. We have written two recursive methods, print1 and print2. One of these methods prints numbers from 1 to n and the other prints numbers from n to 1. We'll trace these two methods and see which one prints from 1 to n and which one prints from n to 1. First, we'll trace this method, print1. First, we have called this method with argument 3. So in the first call, value of n is 3. Now this method executes, n is printed, so 3 is printed. Now this print1 is called with argument n minus 1. n is 3, so it is called with argument 2. Now this 2 is printed and it is called with argument 1. Next, this 1 is printed and it is called with argument 0. Now this condition is true. So we have reached the base case. So the winding phase stops and unwinding phase starts. So control comes here, 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 and finally here. So we can see that This method prints numbers from n to 1. Now let's trace the next method, print 2. Initially this method is called with argument 3. So in the first call, value of n is 3. Next, this method is called with argument n minus 1. So in the next call, value of n is 2. In the next call, value of n is 1. And in the next call, value of n is 0. Now n is 0, so this condition becomes true. We have reached the base case. Now the control will return. So we'll come here. Now in this call, value of n is 1. So 1 is printed. Next, we return here. In this call, value of n is 2. So 2 is printed. Next, we return here. In this call, value of n is 3. So 3 is printed. And finally, we return here. So we can see that this method, print 2, prints the numbers from 1 to n. These are the two methods, print 1 and print 2, that we have seen. And we have called these methods here in main. Now let's run this program. So we can see that the method print1 prints numbers from n to 1 and the method print2 prints numbers from 1 to n. In this video, we'll see how to find out the sum of digits of an integer recursively. Suppose we have to find sum of digits of this number. We can find it by adding 7 to sum of digits of 2658. This 7 is the least significant digit of this number, and this 2658 we got by removing this least significant digit. Now sum of digits of 2658 can be found out by adding 8 to sum of digits of 265. Similarly, we can write this, and this is our base case. Sum of digits of a single digit number is the number itself. So this is the base case and this is the recursive case. In the recursive case, sum of digits of n can be found out by adding least significant digit of n to sum of digits of n without the least significant digit. Now to find out the least significant digit, we can write this expression n modulus 10. And to remove the least significant digit of n, we have to divide it by 10. The base case is when n has only one digit. And n will have only one digit if n by 10 is equal to 0. Now this is our recursive method. If n by 10 is equal to 0, that is if n is a single digit number, then sum of digits is the number itself. So in this case, n is returned from this method. Otherwise, sum of digits of n by 10 and n modulus 10 is returned. This n modulus 10 is the least significant digit of n, and this n by 10 is a number n without the least significant digit. Now let's trace this method. In the first call, value of n is 2658. Now this method is called with argument n by 10. N is 2658, so n by 10 is 265. So in the next call, value of n is 265. Similarly, the next call, value of n is 26. In the next call, value of n is 2. Now we have a single digit number, so this condition becomes true. We have reached the base case, so the winding phase will stop and unwinding phase will start. So 2 is returned from this method. The value of this call is 2 and n modulus 10 is 6. So 2 plus 6 is returned from here. The value of this call is 8 and n modulus 10 is 5. So 8 plus 5 is returned from here. Value of this call is 13 and n modulus 10 is 8. So 13 plus 8 is returned from here. So this is how we find out sum of digits of a number recursively. Now let's see this method in a program. This is the recursive method for finding sum of digits of this number n. We've called this method here in main. Now let's run this program. In this video, we'll see how to write a recursive method to print a decimal number in binary, octal and hexadecimal forms. First we'll see how to print a decimal number in binary form. For this, the decimal number is repeatedly divided by 2 till it is reduced to 0. And the remainders are printed in reverse order. Suppose we have to print this 13 in binary form. So 13 is divided by 2, remainder is 1. This 6 is divided by 2, remainder is 0. 3 is divided by 2, remainder is 1. This 1 is divided by 2 and remainder is 1. Now these remainders are printed in reverse order. So this is the binary form of this number 13. This is a recursive method that prints a decimal number in binary form. Now let's trace this method. First time when this method is called, argument is 13. So in the first call, value of n is 13. Now this method is called with argument n by 2. So in the next call, value of n is 6. In the next call, value of n is 3. In the next call, value of n is 1. And in the next call, value of n is 0. Now this condition becomes true. Winding phase stops and unwinding phase starts. So control will return here. Now in this call, value of n is 1. 1 modulus 2 is 1. So 1 is printed. Now control is returned here. In this call, value of n is 3. 3 modulus 2 is 1. So 1 is printed. Now we return here. Value of n is 6. 6 modulus 2 is 0. So 0 is printed. We return here. Value of n is 13. 13 modulus 2 is 1. So 1 is printed and then we return here. So this is how this method works. Now let's see this method in a program. This is the method that we have just seen. And this method convert base will print n in binary, octal or hexadecimal form depending on the value of this second argument. In this method main, we have called these methods here. Now let's run this program. In this video, we'll see how to find the nth power of a number recursively. Suppose we have to find fifth power of this number, 38. Now we can write 38 to the power 5 is equal to 38 into 38 to the power 4. And this 38 to the power 4 can be written as 38 into 38 to the power 3. Similarly, we can write these statements. Now we know that any number raised to the power 0 is 1. So this acts as the base case. So this is our base case and this is the recursive case. This is the recursive definition and this is the recursive method for finding nth power of a number x. Now let's trace this method. In the first call, value of x is 6 and value of n is 4. Now in the next call, value of n will be 3. In the next call, value of n will be 2. In the next call, value of n will be 1. And in the next call, value of n will be 0. Now this condition is true. We have reached the base case. So this winding phase stops and unwinding phase starts. And 1 is returned from here. Value of this call is 1 and x is 6. So 6 into 1 is returned here. Value of this call is 6. X is 6. So 6 into 6 is returned here. Value of this call is 36. X is 6. So 6 into 36 is returned here. Now value of this call is 216 and x is 6. So 6 into 216 is returned here. So this is how we find the nth power of a number recursively. Now let's see this method in a program. This is the recursive method for finding nth power of this number x. And in main we have called this method here. Now let's run this program. In this video, we'll see how to find greatest common divisor of two numbers using Euclid's algorithm. Now, greatest common divisor of two numbers a and b is equal to a if b is equal to 0. Otherwise, it is equal to greatest common divisor of b and a modulus b. Now, suppose we have to find greatest common divisor of these two numbers 36 and 22. This is equal to GCD of 22 and 14 because 36 modulus 22 is 14. This 22 comes from here. This is equal to GCD of 14 and 8 because 22 modulus 14 is 8 and 14 comes from here. This is equal to GCD of 8 and 6 because 14 modulus 8 is 6 and this 8 comes from here. This is equal to GCD of 6 and 2 because 8 modulus 6 is 2, 6 comes from here. This is equal to GCD of 2 and 0 because 6 modulus 2 is 0 and this 2 comes from here. Now we have reached the base case. The value of B is 0. So GCD will be equal to the value of A. Value of A here is 2. So GCD is equal to 2. Now suppose we have to find GCD of these two numbers. This will be equal to GCD of 35 and 21, because 21 modulus 35 is 21. This 35 comes from here. This is equal to GCD of 21 and 14, because 35 modulus 21 is 14. 21 comes from here. This is equal to GCD of 14 and 7. This is equal to GCD of 7 and 0. Now we have reached the base case. So GCD is equal to 7. Now this is the recursive method for finding greatest common divisor of two numbers A and B. It is a simple translation of this recursive definition. Now we'll trace this recursive method. In the first call, value of A is 36 and value of B is 22. In the next call, value of A is 22 and value of B is 36 modulus 22, which is 14. In the next call, A is 14 and value of B is 22 modulus 14, which is 6. In the next call, value of A is 6, value of B is 14 modulus 6, which is 2. And in the next call, value of A is 2 and value of B is 6 modulus 2, which is 0. Now this condition becomes true. We have reached the base case. So this winding phase will stop and unwinding phase will start. So this value of A will be returned from here. This 2 will be returned from here. It will be returned here, 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 and here. So this value 2 will be returned to the original function call. Now we'll see this method in our program. This is the method that we have just seen. And in main, we have called this method here. Now let's run this program. In this video, we'll see how to find out the nth Fibonacci number recursively. This is the Fibonacci series. The 0th Fibonacci number is 0. The first Fibonacci number is 1. And all other Fibonacci numbers can be found out by adding the previous two numbers. For example, the second Fibonacci number can be found by adding these two numbers. This third Fibonacci number 2 is 1 plus 1. This fourth Fibonacci 3 is 2 plus 1. This 5 is 3 plus 2. This 8 is 5 plus 3. This 13 is 5 plus 8, and so on. Now this is the recursive definition of finding the nth Fibonacci number. The 0th Fibonacci number is 0. First Fibonacci number is 1. And all other numbers can be found out by adding the previous two Fibonacci numbers. So these are the two base cases and this is the recursive case. This is the recursive method for finding nth Fibonacci number. We can see that we have two recursive calls here in this function. This type of recursion is also called binary recursion. The examples that we have seen till now had linear recursion. Now suppose we have to find the fifth Fibonacci number. To find it, we have to add fourth and third Fibonacci numbers. To find this fourth Fibonacci number, we have to add third and second Fibonacci numbers. To find this third Fibonacci number, we have to add second and first Fibonacci numbers. And to find the second Fibonacci number, we have to add first and 0th Fibonacci numbers. Now these two are the base cases. The first Fibonacci number is 1 and the 0th Fibonacci number is 0. So if we get this second Fibonacci number by adding these two, this first Fibonacci number is 1. So we get this third Fibonacci number by adding these two. Here again we'll compute this second Fibonacci number. Now we get this fourth Fibonacci number by adding these two. Now here again we'll compute this third Fibonacci number. Comes out to be 2. Now we get this fifth Fibonacci number by adding these two. We can see that this implementation is very inefficient because the same computations are being performed many times. For example, we are computing this third Fibonacci number here and here also. Now we'll use this method in a program to print Fibonacci series. This is the method for finding nth Fibonacci number recursively. And in main, we have called this method here to print the Fibonacci series. Now let's run this program. In this video, we will see how to solve the Tower of Hanoi problem recursively. In this problem, we have to move disks from one pillar to another using a temporary pillar. Suppose we have these three pillars A, B and C, and we have some disks placed on pillar A, and these disks are placed in decreasing order. That is, the largest one is at the bottom and the smallest one is at the top. Now these disks have to be placed on pillar C in the same order. And there are two conditions. The first one is that only one disk can be moved from one pillar to another at a time. And the second condition is that the larger disk can never be placed on top of a smaller disk. We can use this pillar B as a temporary pillar for placing the disks temporarily whenever required. So A is the source pillar, B is the temporary pillar, and C is the destination pillar. Now we'll see the solution of this problem for n is equal to 1, 2 and 3, where n is the number of disks placed on pillar A. First, let's see the solution for n is equal to 1. There is only one disk on pillar A. So in this case, solution is very simple. We just have to move this disk from A to C. And this will be the base case of our problem. Now we have to identify the recursive case. For that, first we'll solve the problem for n is equal to 2 and n is equal to 3. Now let's solve the problem for n is equal to 2. In this case, we have two disks on pillar A, and these disks have to be moved to pillar C in the same order. So first we'll move this upper disk from A to B. Then we'll move this lower disk from A to C. Then we'll move this upper disk from B to C. So this is the solution for n is equal to 2. We move the two disks from A to C using B as a temporary pillar. Now let's see the solution for n is equal to 3. Now n is equal to 3. So there are three disks on pillar A, and these three disks have to be placed on pillar C in the same order. Now this largest disk should be at the bottom of this pillar C. So first we'll place these two upper disks on pillar B and then move this largest disk from A to C. Now for placing these two upper disks on pillar B, we'll use C as a temporary pillar. So first we'll move this upper disk from A to C. Next we'll move this disk from A to B. Next we'll move this disk from C to B. Now we have placed the two upper disks on pillar B. Now we can move this largest disk from A to C. Now the next task is to place these two disks on pillar C. Now for doing this, we'll use pillar A as a temporary pillar. So first we'll move this disk from B to A. Next we'll move this disk from B to C. Next we'll move this disk from A to C. So this is the solution for n is equal to 3. We have seen that we have broken our task into three parts. The first part is moving two upper disks from A to B using C as a temporary pillar. In the second part, we move largest disk from A to C, and in the third part, we move two upper disks from B to C using A as a temporary pillar. Now if n is equal to 4, then first we'll move these three upper disks from A to B using C as a temporary pillar. Next we'll move this largest disk from A to C. Next we'll move these three upper disks from B to C using A as a temporary pillar. Now if we have n disks, then we'll move upper n minus 1 disks from A to B using C as a temporary pillar. Next we'll move nth disk from A to C. And next we'll move n minus 1 disks from B to C using A as a temporary pillar. So this is the recursive case of our problem, and the base case is when n is equal to 1, when we have to move only one disk from A to C. This is the recursive definition for Tower of Hanoi problem. The base case is when we have to move only one disk from source pillar to destination pillar. In the recursive case, first we move n minus 1 disks from source pillar to temporary pillar using destination pillar as a temporary pillar. And then we move nth disk from source pillar to destination pillar. And then we move n minus 1 disks from temporary pillar to destination pillar using source pillar as a temporary pillar. This is the recursive method for Tower of Hanoi problem. we'll trace the method calls for n equal to 4. We have to move 4 disks from A to C using B as a temporary pillar. For this, first we'll move 3 disks from A to B using C as a temporary pillar. Then we'll move the 4th disk from A to C. Then we'll move the 3 disks from B to C using A as a temporary pillar. Now for moving 3 disks from A to B using C as a temporary pillar, first we'll move 2 disks from A to C using B as a temporary pillar. Then we'll move the 3rd disk from A to B. Then we'll move 2 disks from C to B using A as a temporary pillar. Now for moving these 2 disks from A to C using B as a temporary pillar, we have to move 1 disk from A to B using C as a temporary pillar. Then we will move 2nd disk from A to C. Then we have to move 1 disk from B to C using A as a temporary pillar. Now these two are the base cases since value of n is 1. So here we'll just move the disk from A to B, and here we'll move disk from B to C. Similarly, other calls will also proceed. These all are base cases because the value of n is 1. This is the recursive method for solving Tower of Hanoi problem. And in main, we have called this method here. Now let's run this program. This is a solution for 1 disk. This is a solution for 2 disks. This is a solution for 3 disks. And this is a solution for 4 disks. In this video, we learn about tail recursive calls and tail recursive methods. A recursive call is tail recursive if it is the last statement that is executed inside the method. For example, in this method, this recursive call is a tail recursive call because it is the last statement to be executed inside this method. While here in this method, this recursive call is not a tail recursive call because it is not the last statement that is executed inside this method. Now in methods that return a value, a tail recursive call is a recursive call that appears in the return statement but is not part of an expression. For example, in this method, this recursive call is a tail recursive call because it appears in the return statement but is not part of any expression. While in this method, this recursive call is not a tail recursive call because it is part of this expression. In this method, we have 2 recursive calls. The first recursive call is not a tail recursive call, while the second recursive call is a tail recursive call. In this method also, we have 2 recursive calls, but here both of them are tail recursive calls. Now a method is tail recursive method if all the recursive calls in it are tail recursive. So these are some examples of tail recursive methods. In a tail recursive method, there is nothing to be done in the unwinding phase. For example, in this method print 1, there is nothing to be done in the unwinding phase. Similarly, in this method GCD, there is nothing to be done in the unwinding phase because the return value of the last call is the value of the original call. Most of the repetitive problems can be implemented using either iteration or recursion. So in this video, we'll compare the two approaches. In both iteration and recursion, the same code is repeatedly executed. In loops, repetition occurs when the block of code is finished or when a continuous statement is encountered. In recursion, repetition occurs when the function calls itself. In loops, variables inside the loop are modified using update statement, and in recursion, new values are passed as parameters to the next recursive call. To stop execution of a loop, there is a terminating condition and the loop proceeds in such a way that this condition becomes true at some point. And to stop recursion, we have a base case and the recursive functions proceed in such a way that we finally reach the base case. Now recursion involves many function calls, so it requires more time and space as many activation records have to be pushed and popped from the runtime stack. In iteration, there is no such time or memory overhead. For some problems, iterative algorithms are harder to implement, while recursive ones can be easily defined. For example, the Tower of Hanoi problem can be easily solved recursively, while the iterative version is harder to implement and understand.